Another important point function that it is worthwhile to review is what we call the shifted point impulse function, or the shifted point impulse signal. Now, the shifted point impulse is represented by a shifted Dirac delta function. A shifted Dirac delta function is represented by delta x minus x naught. This right here is equal to 0 as well as infinity. It's equal to infinity for all x equal to x naught, and it's equal to 0 for all x not equal to x naught. Why is this important? This is important especially when we talk about the COM function. Now keep in mind that if the integral from negative e to e of delta x minus x naught dx, this will be equal to 1. So what this means is that if we multiply a function x by delta x minus x naught and we integrate across all points in space, we will pick off that function at the point x naught. At the point x naught. This is crucial and this is very critical. So to illustrate the difference between a point impulse and a shifted point impulse, we will draw this diagram. This is x. This is x. So for point impulse, the value of delta x is at the origin. This is delta x. For a shifted point impulse, this is x naught, this is 0. This is the delta x minus x naught. You realize that the function has been shifted to the point x naught. And so when you multiply delta x, f by delta x, you will get f naught as long as you integrate this across all points in space. But if you multiply f of x by delta x minus x naught dx and integrate across all points in space, you will pick up the value of that function at x naught. These concepts are really important in sampling. Really important in sampling, and we're going to actually discuss this for the future, in the future. Now, in a two-dimensional case, in 2D, the Dirac delta function essentially is defined as delta x y. This still is equal to 0 and infinity. This is equal to infinity at x equal to 0 and at y equal to 0. And this is 0 at x not equal to 0 and y not equal to 0. This is the Dirac function, or the point impulse function, in 2 dimensions. Similarly, if we multiply the function f of x by delta x y, remember it is in 2 dimensions. If we integrate across all space, this is minus x plus delta infinity. minus infinity plus delta infinity dx dy, we will have the function f 0, 0. In other words, if we multiply any signal by the Dirichlet delta function or the point impulse function and integrate across all points in space, we will pick up the value of that signal at the origin. You will pick up the value of that signal at the origin. Now, before we move on to the next function that is very important, it is worthwhile to review some important characteristics of the point impulse function. One, delta AX is equal to 1 over the magnitude of A delta X. 2, we will later on, as the lesson progresses, look at some of the application of this property. The delta minus X is just going to be equal to delta X. 3, you have f of X delta X is equal to f naught of X delta X. Property 3 is very important. It's very important because this implies that the integral from negative infinity to positive infinity of f of X delta X dx is equal to the integral from negative infinity to positive infinity of f naught of X delta X dx. This is equal to f naught of X, the integral from negative infinity to positive infinity of delta X dx. And if you remember, this here is equal to 1, so all of this is equal to f naught of X, which really is an important property as far as sampling of signals in medical imaging is concerned. The next property that you need to bear in mind is that the fourth property, if f of X is continuous. If f of X is continuous, then f of X delta X minus X naught will be equal to f of X naught delta X minus X naught. Property 4 is very important. Per property 4, it means that if you integrate across all points in space of f of X delta X minus X naught dx, this will be equal to this will be equal to the integral of minus X f X naught delta X minus X naught dx. This is a constant, so that can go out. This becomes f of X naught, the integral of minus infinity to plus infinity delta X minus X naught dx. And what do we know? This is equal to 1, so this is just equal to f X naught. So what this means exactly is that if we multiply a function by a shifted point function, we will be able to pick off the value of that signal or function at that particular point where it is shifted. In other words, if we shift our point impulse function from the point X to X naught, then we will be able to pick up the value of that signal at this particular point. This is crucial in sampling. This is very crucial in sampling. And lastly, And lastly, this means that we can represent our function f of x as the integral from negative infinity to positive infinity of f tau delta x minus tau d tau. Now, what happens in two dimensions? What happens in two dimensions? Now, in 2D, the point function is defined as x, y. Remember, we did this a little bit above. This is equal to 0, infinity. This is for all what? X not equal to 0, y not equal to 0. This is for all x equal to 0 and y equal to 0. It is worthwhile for you to keep in mind that this means that the integral from negative infinity to positive infinity, we're dealing with a double integral because we are working in two dimensions of f of x, y, delta x, y, dx, dy. The order doesn't really matter. This will be equal to f of 0, 0. So it works the same. It works the same in two dimensions as in one dimension. So if we shift a Dirac delta function from a point x, y to a point, let's say x minus epsilon y minus the squiggly symbol, that is from what then happens? Then our signal, just like we did above, is given by f equal to the integral from minus infinity to positive infinity, the double integral of f x y delta x minus epsilon y minus the sine dx dy. This equation right here will define our signal in two dimensions. Will define our signal in two dimensions. This property is very important, and we call this the shifting property. And we call this the shifting property. We call this the shifting property.